In this video, we are diving into Kafka. First, by understanding conceptually what Kafka is and why it was developed to solve what problems exactly, and then get hands-on with a simple but realistic demo project where we will build a Python application that uses Kafka for a simple use case. It will be a step-by-step guide to make sure you can follow smoothly and understand every step clearly. And of course, you'll find the code repository and other relevant links in the video description. Now first, let's understand quickly why Kafka was even created using real-life examples that will make everything click for you. Imagine we're building an e-commerce application called Stream Store with microservices handling payments, orders, inventory, and so on. And every time a customer places an order on our online store, like they bought a t-shirt or a bracelet or whatever, that event triggers a chain reaction, like t-shirt stock needs to be updated now because we just sold one. A confirmation email is sent to the customer, invoice is generated, and our sales dashboard gets updated with a new revenue number. But we are a small startup, so we begin with a simple architecture where microservices for orders, payment, invoice, and so on just directly call each other. And this works fine until our online store becomes really popular. Plus, we announce Black Friday sales, and suddenly, with thousands of users placing orders and checking out all at the same time, our application crashes under load. Here's what's happening. We have tight coupling between the microservices. So that means if payment service crashes, the entire order process freezes because it depends on the payment service to respond. The services have synchronous communication, which means when order service sends a request to a payment service, it then waits for it to reply. And if it doesn't reply or is slow in reply because it's overwhelmed and overloaded, it just waits and hangs there. And the front-end service that called the order service is now waiting for order service to respond. So one slow service slows the entire application down. And if one service fails, it causes disruption in the whole application. Plus, in that time of outage, we lose all the valuable analytics data. But what if instead we redesigned the system in a way that the orders flowed through our online store like items on a conveyor belt? And this is where Kafka comes in. Think of Kafka as a middleman between these microservices. So instead of services talking to each other directly, they use Kafka as a middleman to communicate. The order service hands an event to Kafka saying, hey, an order was just made with these details. Can you just let all the other services know? And it just continues its work without waiting for a reply. So it doesn't wait there to make sure the payment and other services receive that information. It trusts that Kafka, as broker, will deliver that message. And in Kafka, the services that create these events and hand it over to Kafka are called producers. And the events themselves are simple structures with key value pairs and some metadata about when the event was created, which service created it, and so on, which can later be used for analytics. Now, where do these events get saved? Well, Kafka organizes all the events into topics. So instead of dumping everything in one bucket, they get organized logically. So you may have an orders topic, inventory topic, and so on. So you, as an engineer, decide what topics to create based on your application needs, similar to creating a database schema. On the other side, we have consumers. These are microservices that are subscribed to these topics, which means whenever a new event appears inside a topic that a producer created, the consumers that subscribed to that specific topic get notified by Kafka that there's a new event, and these microservices then process that event. For example, as soon as orders topic gets an event that new order was placed, a notification microservice will take that event and send a confirmation email. An inventory service will update product stock and maybe generate new inventory events. A payment service generates invoice, and so on. So all these microservices do their work based on that new event. Now, it's important to highlight that Kafka is not a database replacement. Instead, think of Kafka as a tool that enables chain reactions where one event triggers multiple actions, including creating other events or updating the actual database. And it also naturally enables real-time analytics. Think of live sales dashboards or driver location updates in Uber or similar apps. Those are typical use cases for Kafka, especially for applications that produce massive amounts of data live. So with millions of users generating millions of events, how does Kafka maintain performance? Because Kafka was built to be scalable when we have massive loads of data or events being generated in an application. So how does Kafka achieve that scalable performance? Well, one main component of that is partitions. To understand partitions, imagine having a video production team where one editor edits all the videos, but as you expand, you need to hire more editors because you are producing more videos. And now you can decide to assign one editor specifically to only the short videos. And you have one editor for long-form videos. And then you have another one for podcast episodes. Same way, if you have an orders topic, you can actually create partitions within for EU orders or US orders or Africa orders and so on. And you will have one consumer handle the EU orders, another process US orders and so on. So they all get processed in parallel. And now let's say US orders are suddenly 100x more than the other two. You can keep the performance by adding more consumers for that partition. Same way as if you had suddenly 100 times more short videos to edit, you would just add another editor for short videos specifically. So you have a team of 4 people doing just the shorts. And these are called consumer groups. So when you start multiple instances of a payment microservice, for example, they will form a group to process all US orders, for example, and Kafka will distribute that load automatically among them. And finally, the data itself, those events, is stored on Kafka servers called brokers that persist every event as long as it's needed. And this is actually what makes Kafka different from standard message brokers. This means with Kafka, events or messages do not disappear once it was consumed by the consumers. They persist on disk, so it can be read multiple times, it can be read by multiple different consumers, and it can be used later for analytics. Whereas traditional message brokers are like TV programs. If you miss something, it's gone. You can't replay it. Now, this was a very condensed explanation of Kafka to prepare you for the demo, but I do have a longer, more detailed explainer video on Kafka, which is around 18 minutes, which you can watch right here if you're someone who doesn't want to miss any details. And then you can come back and continue with this video. Now that you understand what Kafka is and how it enables modern microservices applications that need to process lots of data and need to scale for millions of users, let's bring it to life with a hands-on demo that shows exactly how these concepts work in practice. Because you may understand something conceptually, but having experienced it once practically, hands-on, even with a simple example, makes a huge difference. So to make it realistic and add some context to it, we're going to simulate a simple food delivery backend. The kind of system that would power applications like Uber Eats or DoorDash, etc. In our demo, first we will start Kafka instance locally as a Docker container. Then we will use Python to build a small application with 2 parts. We're going to have a producer that simulates a customer placing a food order. It will send that order as a JSON message to a Kafka topic called new orders. And we're going to have a simple consumer that subscribes to that topic and prints out any new orders it receives, representing a backend service like an order processor or inventory tracker, basically a service that processes that new order event. And we're going to be using PyCharm IDE to write our Python programs for producer and consumer. and run all the programs, including the Python applications and Kafka, everything from a central convenient interface to make it super easy for you to follow. So this is going to be a minimal but very realistic example of how Kafka producers and consumers interact with Kafka in a real-world architecture. So let's get started. So first, we're going to create our Python project, and for that, we are actually going to download PyCharm, which is an IDE for Python applications. You can just type PyCharm, download from JetBrains. Just choose the one for your operating system, and there you go. Install PyCharm in our applications, and here we have it. Before we move on, I want to give a huge shout out to the sponsor of this crash course that basically made this video possible for you. PyCharm is the only Python IDE you need, no matter what kind of project you're working on. It comes with out-of-the-box support for Python, databases, Jupyter, PyTorch, TensorFlow, Hugging Face, if you're working with data science or AI, Django, Flask, Git, and more. It also has a built-in context-aware AI assistant and smart coding agent called Junie, which literally helps you move faster from idea to implementation. So whether you're building web applications, data pipelines, whether you're working on machine learning modules or full AI systems, PyCharm can handle all of it. So you can download PyCharm to not only follow along this demo, but to also use it for all your projects. And the best thing about it is that it's free forever. And if you use the link that we provide in the video description, you will actually get 1 month of Pro version included. So you can even test out the Pro features for free. So use the link, or you can directly scan this QR code here. And let's move on. So let's open the IDE, and this is our fresh installation view. And we're going to create a new project. And this is going to be a Python project, and let's call this Stream Store. That's the name for our imaginary application that we're building. We're going to use the defaults. So PyCharm actually gives you built-in Python virtual environment for your project. And you can choose the latest Python version. If you don't have it locally yet, you can just select it here and PyCharm will automatically download it in the background. And that's it. We are good to go. Create our project. Great. So this is our empty project. Let me zoom in a little bit. And let's get started. So the first step in our demo is going to be to basically just start Kafka locally on our machine so that our application can connect to Kafka by sending in events as well as consuming those events that Kafka stores. And we're going to start Kafka as a Docker container with Docker Compose. So going back, I'm going to look up Kafka image on Docker Hub. So this one is from Confluent, official image for Kafka. And we're actually gonna use the latest tag 7.8.3. So that's the image we're gonna use. And this is a version of Kafka that uses the built-in K-Raft. So in my other Kafka explainer video, I actually explained that in the older versions, Kafka was dependent on Zookeeper, which is an open source project, an external project that was used to manage and orchestrate Kafka brokers. In newer versions, Kafka has this functionality built in with a feature called K-Raft. So that's what we're going to get with the latest image. So in our project, we're going to create a new file for Docker Compose, and we're going to define how to run Kafka in there. So let's call it Docker Compose. YAML, and I'm gonna paste in the basic configuration. This is the version for Docker Compose, and this is the Kafka container configuration. So we're starting Kafka container on this port. We're going to call it a Kafka, and this is the image with this tag. And we also need to provide a few environment variables to our Kafka service for it to run properly. And we get this auto completion in PyCharm as well for different configuration languages and programming languages, which is pretty convenient. And let's go through each environment variable one by one and explain what it is. So first of all, we're gonna set Kafka kraft mode to true. As I explained, kraft is basically Kafka's built-in system that allows Kafka to manage its own metadata and the Kafka cluster coordination internally and so on. So kind of do the operations work of the Kafka brokers and so on. And as I said, in early versions, Kafka used this open source project called Zookeeper, which meant that you would need to install and configure that in addition to Kafka. But in versions starting from 3, actually, that dependency on this external tool was removed and replaced by building that feature into Kafka itself, which is simpler and a preferred way of deploying Kafka for modern setups, actually. So kraft is basically a new part of Kafka that lets it manage and operate itself. Great. The next thing we need to do, or we need to configure, is set the cluster ID. And I've just created this random string. So it's not an integer, it's basically a random arbitrary ID. And Kafka node ID, which is an integer, we're gonna set it to 1. So what are these two values and what do they actually do in the configuration? So Kafka is designed to run as a cluster made up of multiple nodes. And these nodes are called Kafka brokers. You remember I mentioned that brokers store and manage the data, those events that are created and consumed, organizing them into topics and partitions under the topics. And these brokers handle requests from producers that are sending the data and consumers which receive the data or which read the data from Kafka. And in a production environment, you will have a Kafka cluster with multiple brokers that work together instead of just one broker, because you want to have fault tolerance and scalability and not just be dependent on one node, right? Because if that crashes, then you don't have the service anymore. So Kafka in production mode will be deployed as a cluster. And that cluster has an ID that basically all those brokers underneath share. And one of those brokers is going to have a role of what's called a controller. The controller is basically responsible for managing the cluster's state. So that's kind of the big boss, the manager of everything. It tracks which broker is the leader for each partition, reassigning partitions in case of broker failures, and basically handling all the cluster administration tasks. And at any given time, only one broker is an active controller. So if that broker crashes, another broker will take over as an active controller. Now, in our case, for simplicity, we're deploying a one broker Kafka cluster. So we're going to have just one broker, which will also act as a controller. So the cluster ID is for Kafka cluster, and the node ID is for that one broker that we are deploying. And its ID is integer, so we're going to assign it 1. Then we have another configuration that's called Kafka process roles. So let's explain that one as well. This configuration tells Kafka that this node that we're defining here will act both as a broker and controller. As a broker, it will store and serve the data. As a controller, it will manage the cluster coordination. And in kraft mode, a node can play either or both roles. So we're setting this here as well. Then we have an environment variable called Kafka controller quorum voters. So what is that? This basically defines which brokers are controllers and can vote on important cluster decisions. And in our case, we only have one controller, which is node 1, which is running or accessible at Kafka port 9093. And if we had more brokers who had controller role, you would basically list them all here, right? So you would have 2 ID of the second broker accessible at this address. Now, as I said, you only have one active controller at any time. So just one of them will be the active controller. However, for redundancy and fault tolerance, we can define a group of controllers. So you still have one active controller or the leader of the group that is managing the cluster. And the rest are kind of like backup controllers that participate in consensus as passive voters and are ready to become the leader if the active controller fails or crashes, basically. The next one we have is called Kafka offsets topic replication factor. And this is actually very important and a required attribute. Otherwise, our application will not work. So what this means is when we set the replication factor to 1, which is what we're going to do, this means that there is only one copy of the Kafka metadata that keeps track of which messages each consumer has read. If our Kafka goes down, the tracking data, again, meaning Kafka knows and tracks which consumers have read which events from which topic. So that's the metadata that it kind of keeps as a journal. And setting it to 1 means that there's no backup for that metadata. So if Kafka crashes, that metadata is lost, basically. So in simple words, replication factor 1 means no backup, just one copy. And in production environment, of course, to make sure data is not lost, you would set this number higher so that the metadata is actually replicated in Kafka and it's stored in multiple locations. So if we do not explicitly set it to 1, by default, it's actually 3. That's the default value for a cluster of 3 nodes. But since we are running just one node, we're gonna need to set it at 1 as well to override the default. Otherwise, it's gonna give us some problems while using Kafka. We have 4 more environment variables to configure. So let's add them one by one. Next one is Kafka listeners. So this tells Kafka to open 2 doors. One for regular data traffic on port 9092, where Kafka is accessible. So that's going to be plain text protocol. This is where producers and consumers connect to Kafka, right? Write the data, read the data. So that's one endpoint where Kafka listens or is accessible for producers and consumers. And then we have another one, like a special endpoint or door for controller communication on port 9093, right? That's where the brokers communicate with each other. So that's node-to-node management configuration, right? Which they use to do the administrative stuff and so on. So one door for clients and one for controllers. Then we have another variable called Kafka advertised listeners, which then tells the clients they're supposed to talk to Kafka explicitly, saying, hey guys, this is the address where you can talk to me. And in our case, this is going to be localhost because we're going to run it locally on port 9092. So this is advertised, or basically what Kafka explicitly tells clients to connect at this endpoint. And then we have the same thing for controllers. That again tells controllers explicitly use, and this is the shortcut for the URL, use the controller door with this URL for all controller to controller talking and voting. So this makes Kafka controllers use this special controller door just for their own management communication. And finally, the last configuration we're going to set is Kafka log directory, which tells Kafka where to store all of its data files, like broker logs, controller metadata, and so on our computer's disk, right, where the Kafka is running. So in our case, we're gonna let it store in this folder, So that's where all the data is going to be, which is in Kafka running environment, which is the container, the Docker container. And talking about data that Kafka generates and stores, we also want to persist the data locally on the computer, right? So whenever we run Docker containers, they have this virtual Docker file system where everything gets stored. And if the container is removed, if we create a new container, all the data is gone. So if we want persistence, we need to configure volumes, which is just Docker concept. So we're gonna create a volume here. We're gonna call it Kafka kraft or Kafka data. We can call it whatever. And then we're gonna configure here at the same level as environment volume or volumes. And so this is gonna be volume on our computer, and that will be bound to where Kafka actually stores all the data. So this is the path inside the container where Kafka service actually will store data by default. So you can actually look up this path inside the container in the documentation, and then we are basically replicating or saving that, persisting that on our local computer with this volume. And that's it. That's our Kafka configuration for local environment. And once ready, we can actually start Docker service first of all. So make sure you have Docker running. There you go. Docker is up and running. And what we can do actually is go to services, or directly here, as you see in PyCharm, you have these triangular icons which let you start services. So if I click here, it will execute docker compose up command in background, as you see, and it will start all the services defined here. We just have one service, so it's gonna start that one. So just click here, or you can also right click and start with the run docker compose, which is basically the same as going to the terminal and executing docker compose up, right? But we can do it directly from here. And as you see, container Kafka started and it's running in the background. And if I do docker ps, we should see our Kafka container running. Perfect. Awesome. Now that we have Kafka up and running, we can actually write our first producer that will generate an event. So we're simulating a food delivery application. So our producer will basically be an order service that will create an event every time a food order is placed on our website and send that event to Kafka for any consumers in the backend to process that event. So that's going to be a Python program, and let's call it producer.py, which is a technical name. You can also give it or like a logical name, like new orders. And the first thing we need to do is to install a Python library for Kafka connection. So for our Python application to communicate with Kafka, we need a Python library for Kafka that basically has the functions and interface to make those requests. And that library is called Confluent Kafka because that's the service we're using. And we can actually install it directly here in our virtual isolated Python environment, as you see right here. And let's do pip3, which is Python's package manager, install Confluent Kafka. That's the name of the library. Let's execute. And there you go, successfully installed. The newest version, successfully installed. And you can actually see it in your project's external libraries. So site packages, there you go, we have Confluent Kafka. So we can validate that it was actually installed, and we have it available now to use in our project. And the first thing we're going to do is basically just import the producer from the library that we can use to produce events. So from Confluent Kafka, which is the library name. We're going to import producer. And as you see, PyCharm is trying to guess and help us with the import, which is again convenient. And there you go. And now we can use that producer. And again, we're having the auto suggestion here. If you click on tab key, actually, you can take over the suggestion, which I'm going to do now. And that's the configuration we're using. So basically, we're creating new Kafka producer configuration, and we're telling it where Kafka is accessible. Remember this advertised listeners for the clients, localhost 1992. So that's where the producer or Kafka client can talk to the Kafka server. So we're configuring it here in the code. And this is the value for bootstrap.servers. Bootstrap term basically refers to Kafka using this address, this one here, to discover all the brokers in the cluster. So all the Kafka nodes or servers will be accessible at this address. It's not the most intuitive name, but that's how it's called. So with this configuration, we're simply telling producer, if you want to send the events that you produced to Kafka, this is where you can send it to. And we're saving that producer instance that we're creating here in a variable. Let's actually call it producer with lowercase. And we can use that variable now to send the events. As an alternative, maybe just a personal preference, we can save this separately as, we can call this producer config. And again, let's autocomplete. And we are creating producer with this config. So later, if we want to extend this configuration, add more details, then you can do it directly here. Awesome. As a next step, let's actually create and prepare an event that we're going to send to Kafka as a producer, which is going to be a very simple JSON structure. Let's call it order and take over some of the suggestion from PyCharm. So we have order ID, and let's create a unique ID using UUID library or function. That works. And we need a string here, so we can just turn it into a string. And this is a Python library, a built-in library. It says unresolved reference, so I just click on import, and we're going to see it right here. There you go. So this basically generates just a random unique identifier. We are turning it into a string because we need a string version of that and setting it as order ID. Let's say for each order, we also have the user. So I can log into this account and order stuff on there. And that's my username. Then let's say we also have an item, basically what I ordered. Let's say it was a mushroom pizza. And finally, we have the quantity. Let's say I ordered to share, and that's our order data. And that's how events look like. We have simple key value pairs list that carry some information about that event. So this is the actual data we're going to send to Kafka or to consumers actually in the backend through Kafka. But first, this is a JSON object, and we actually need to convert JSON to Kafka compatible format, which is bytes. Again, with built-in functions and libraries, super easy to do. First, we convert this dictionary data type or object data type to a JSON string. So it's going to be JSON dumps. That's the function name. So we're taking the order, and with JSON.dumps function, we're converting this whole thing, this dictionary, into a string representation, and then we're encoding it into UTF-8. So this will basically turn the order dictionary into a string, and this will then encode that string into byte format, which Kafka actually understands or can receive and handle. And we can save that final result into a variable. And there you go. And again, this is a library that we need to import. So there you go. Great. So now we have the event which is ready to be sent to Kafka. And that means let's send it. And again, we have the autocomplete. I'm actually going to write this out so that you can follow. So this is our producer, which already holds the connection to Kafka through this configuration. And we're going to say produce. We're going to say produce. So please produce an event, topic, and value. And actually autocomplete this. So what this does, it sends the value that we have defined here of this event, and it sends to Kafka and says it, please save it or add this into topic called orders. Now, if this topic does not exist yet, because we haven't created any topic in Kafka yet, right? Kafka will actually automatically create a new topic and save this value there. So this does two things in one, creates the orders and then puts this new order event there. And the next time it sends another event, the orders topic will already be there, so it will just be appended or added in the topic. So pretty straightforward, actually. And the final step that PyCharm keeps recommending to us is producer.flush, which is actually a best practice to make sure our program runs cleanly. So what this means is that Kafka producer actually buffers messages for performance. So instead of sending each message and each event one by one, let's say our application is getting hundreds and thousands of orders every hour. Instead of sending each event one by one, it collects 10 events or a group of them and then sends them in batch. And that means if the program crashes or stops at some point, the flush will make sure that all these buffered events that haven't been sent yet get sent before exiting the program. So it kind of forces or flushes those events to Kafka, which is very important because otherwise those events will actually be lost and will never land to Kafka. So all the consumers will miss those events. That's an important addition here and definitely something that you need to implement in production environment. So always call this before the script ends. And talking about handling things when things go wrong and application crashes, as a final step, let's actually add a callback that will track whether our message was delivered successfully or not. Again, when our application sends the events to Kafka, many things can happen on the way. Maybe Kafka crashes, maybe the application crashes, maybe some connection and network error in the middle. So we can add an explicit functionality that tracks whether our message was actually delivered to Kafka or not. And if it wasn't, if there was an error, it logs the error. So it makes the troubleshooting just easier. So what we're going to do, and the way we do it is right here, where we have producer and we have topic to which we're sending the value itself. We can add a callback here. And again, it is suggesting callback. And we can create a function that is executed as a callback. And let's call this function delivery report, because that's what it's going to be. And let's create this function. So right before orders, let's create a Python function, which is going to have, so this is a callback, so it's going to get an error message, which is going to be empty if everything was successful, and the message. And again, going to type it out, and we're going to say if there was an error, we want to see what that error was. And we're going to print out delivery. Yeah, let's actually autocomplete this one. Delivery report error or delivery failed. It's like this, and print out the error message so that we know what actually happened. And if not, so if there is no error, it means that it was successful. And in this case, we can print out, let's do green check. And again, let's autocomplete. And I'm going to say delivered. And we're getting bytes back again. So let's extract the value. Let's convert it back to the string. So that's going to be displayed, which is going to be the order that we sent. Awesome. So that is actually the full producer code that is sending this order to Kafka, and then it is printing out whether it was successful or not. So now, since Kafka is already up and running, we can actually run this producer py and see what happens. So if you right click here, let's do run producer. And we have the output here. Let's close the services actually. And there you go. It says delivered. And this is the value that is printing out, which is the event that we sent. And let's do one more thing. Let's say you want to know exactly what is in that message, because right now I'm reading value and then decoding it. But let's say just, for troubleshooting purposes, you want to inspect yourself what is inside. So we can actually troubleshoot that or log that by printing out this message and all its fields by using dir or directory function. So let's run this again. And as you see, this is the actual directory or all the fields that this message directory actually has, including the partition and offset, which topic this message was actually written to, or which topic it's coming from, the value which we're accessing right here, timestamp, and so on. And here's what's also interesting. Another way to troubleshoot or debug, let's say we have some issues here. Again, you just want to inspect what's happening. If I add a breakpoint here, and let's run this in debug mode instead of run mode. So right here, we have the message. Error is none, so there's no error basically, and the message is not visible. What you can actually do is you can evaluate the expression directly here. We can call this dir message function from this line, and if I execute, I'm going to see the result. And again, that's the value, topic, and so on. So that's actually a pretty interesting way to do the troubleshooting by evaluating any variables directly here. And since we now know which other keys or information we have in this directory, we can actually let this run. We can add another line that tells some additional information about which partition or topic the message was delivered into, and so on. So let's say delivered to message.topic. So that was a function actually. And partition, there you go. At offset message.offset. And now let's run this again. Let's see what we get. There you go. Delivered to orders topic, partition 0, because we haven't defined any partitions inside, at offset 3, because this is the third event or message that we're sending. So that's the offset. If we do it again, there you go. And what we also can do, and I'm actually explaining this and showing this part explicitly because obviously when you're programming, when you're writing an application, you're doing a demo, more than 50% of the time things go wrong. So you need to troubleshoot and check what went wrong, which is an essential skill. And that's why I'm showing you all this troubleshooting side as well. And one important way to troubleshoot is basically check, let's say you are sending these events, but they're not being saved into a topic. So how can we check directly with Kafka if the topic was created and what events are inside? And we can actually check that. Well, since our Kafka is running in Docker container, we're gonna first get the integrated interactive terminal of Kafka. And the name of the container is Kafka. So now we are inside the Kafka container. We can execute this Kafka command. So what comes now, starting from here, is going to be the Kafka commands that you can execute against the running Kafka instance. So Kafka topics. And so this is Kafka CLI. List. So we're going to list all the topics that Kafka has. Bootstrap server, which is what we saw here in the configuration. Local host 9092. That's where Kafka is running inside the container, right? And if I execute this, you see a list of all the topics that Kafka is keeping track of. We just have one, which we created with the first message that we sent right here. And you can also check the events that are in a specific topic. So instead of listing the events, again, we're defining for Kafka CLI where to connect to the Kafka server. And then we're going to say describe. So give us details about topic called orders. So this describes the metadata of the orders topic. So it basically gives you the topic ID, how many partitions it has, we just have one, the replication factor, which we defined in the configuration, in Docker Compose, and so on. And again, if you want to see what other options are available, so this is Kafka CLI. You can check the official documentation. Or directly here in the CLI, we can also do help. And you will see all the available subcommands. And you can see different Kafka commands, including Kafka topics and so on. We have Kafka console consumer. So let's see what subcommands are available here. And this can basically give us, I'm going to clear this a little bit. This can give us a list of all the events in a specific topic. So topic orders. And we have this flag from beginning. So it starts from the first event. Let's execute. And there you go. So we have 1, 2, 3, 4, 5 events actually. We're sending the same stuff. So those are the events inside the orders topic. Again, all these commands that I'm executing here, including the installation and the Docker exit commands, as well as code, everything will be linked in the video description so you can follow along easily. So grab it from below. Awesome. So we have generated a bunch of events which are stored in Kafka. Now it's time to write a program that actually reads those events and processes them as a Kafka consumer. So let's do that as our final step. So now let's write a Python consumer program that listens to any events being added to the orders topic in Kafka. And every time a new event gets added there, it prints out these incoming messages. So it basically reads them out from the topic. So again, it connects to Kafka at the advertised endpoint where Kafka is accepting calls from producers and consumers. It reads out that new event from the orders and it does something with it. In our case, we're just going to print it out just to have a simple use case. But of course, you can do anything once you have the event in the program. So let's create a new Python file, and we can call it consumer, but considering that you may have multiple consumers for the same event, so you can have 3 different microservices that all listen to the same topic events, basically doing different stuff. As I explained before, when a new order comes in, we generate an invoice with an invoice service. We send an email confirmation with an email notification service, maybe update sales dashboard, whatever, right? So instead of consumer, let's call this tracker maybe. So this specific microservice, let's say, it just tracks new events. And in the logic, we're gonna first connect to Kafka broker so that we can subscribe to a topic and then start listening to messages in that topic. And once a new message gets in, we process them one by one. And for consumer, there's the same object as for producer in the same Confluent Kafka library. So if I do Confluent Kafka, it's going to suggest me to import in consumer. And the same way as we defined a connection configuration for producer, we're going to do it for consumer as well. So let's call it consumer config to keep it consistent. And here we're going to define, first of all, the same Bootstrap servers, because we're going to need to connect to Kafka. So that's the first part. Then we're going to need a group ID. So what is a group ID? Group ID basically identifies a group of consumers that are instances of the same program. So these are not tracker and then inventory and other services, but these are multiple replicas of the same tracker application. So let's say for scalability and for high performance, we run multiple instances, which you can easily do with Docker containers. In Kubernetes cluster, for example, you have multiple replicas of the same application. And in order for Kafka to know, these are actually copies or replicas of the same application that all want to read and process the events in parallel for better performance, they are all assigned the same group ID so that they're logically grouped together for Kafka, right? And so if we started 3 instances of the tracker application, they will all get this shared group ID. So Kafka knows this is the same application, just different instances. And it will then distribute the load among them automatically so that they can read those events from Kafka in parallel. And let's call this order tracker ID. So that's how they're going to be called. And finally, let's set the auto offset reset to earliest. So what this configuration does is, in very simple words, the auto offset reset setting tells a Kafka consumer, so it tells our consumer what to do if it cannot find where it last left off reading messages. So in our case, we have 5 events already in the orders topic. So when consumer connects to Kafka and it doesn't see which message it read as the last one, what to do in that case, right? That's the configuration we're setting here. And we're saying with earliest, basically, if you don't know where you left off reading those messages, just start with the earliest. Start with the first one. So it will start reading from the very beginning of the topic, starting with the oldest one and basically processing each event one by one to the earliest one. And with this configuration, we can create a new consumer instance and save it into this variable. And now, so consumer is not sending events, it is subscribing to topics in order to read the events. So we're gonna execute subscribe function. And this is very straightforward. We're just gonna say subscribe to the orders topic. And again, one consumer can subscribe to multiple topics. So this is an array or list. So you can basically just list any topics that the same service wants to subscribe to. Simple as that. And let's add a debugging line here that says, let's find some green emoji. There you go. And let's say consumer is running and subscribed to orders topic. And again, we get auto completion. So now we're going to write a logic that basically tells the consumer to check actively, continuously, whether there is a new event in this order, in this topic that it's subscribed to. And we do that by basically running this continuous loop. And inside, let's actually use autocomplete. And let's explain what this is. So on a continuous loop, over and over again, it polls messages, or it basically pings Kafka asking, is there a new event in this topic that I'm subscribed to or not? If there is no new event, since the last time it read the event, then the message will be none. There's no new event, basically. And in that case, we're just gonna continue. Nothing to do. If, however, there is a new event, but there was an error in reading out or connecting to Kafka or whatever, we also want to handle it. And let's again use our very descriptive emojis. And let's say error. And let's just print out this error message, whatever that is, and continue. All right, so either there is no message, no new event to read from the orders topic, or there is a new event or some kind of message, but there is an error. So in both cases, we are handling them. And in success case, so if there is a new event that consumer hasn't read yet, and there's no error in connection, then we have a success case in which scenario we want to read that value from Kafka and do something with it. So let's first of all save it as a value that we just read from the topic. And as you see, we're decoding it because we're getting the bytes. So we're transforming it into string. And then we can take the string representation of JSON and transform it back to Python dictionary so that we can actually extract the values from it. And we can do that by JSON loads. So we are basically transforming the string to JSON or Python dictionary actually. And let's call this order and let's import JSON. So we have it available. And now we have an actual dictionary representation of the new event that we just read from Kafka. And now you can do whatever you want with that. We're gonna print it out. And let's again do some, let's call it a package or something. Received order. And let's actually extract values from it. So we know the values, what they are. Let's do quantity. And again, this is Python dictionary. And you just use the syntax for accessing values in a dictionary, like this, with square brackets and the name of the key. So we have order this many times, this item from, let's do autocomplete again, from this user. So we have the detailed message of what that order was actually. And one more important thing about the poll and how this works in the background, it's important to understand that Kafka is designed so that consumers ask or poll the broker if there are any new messages, instead of Kafka pushing the messages to them on its own. So this polling actually lets consumers, because the same consumer subscribe to multiple topics, so this polling allows consumers to control how and when and how many times they read those events and messages from different topics. And this could be great for load balancing, for pausing and catching up. So this keeps the protocol simple, it's reliable, it's scalable, and it lets the consumers basically control the speed and duration and frequency of when they consume which events. They can replay events, reread them, and so on. So that means subscribing to topics actually just means that consumer is telling Kafka, I want to read from this specific topic, but the consumer must still poll to actually retrieve new events from that topic, rather than Kafka pushing the messages to our code automatically. So that's just one detail which is important to understand. And now let's do one more thing here actually. So producer program runs, sends the order event and exits, right? This doesn't run in the background. It does its work and it exits. The tracker is still running. As you see, we can stop it, rerun it. It's basically running and listening to the events because we have this while loop, which is running continuously. So what I'm going to do is I'm going to change the order here, simulating that someone else, let's say Nicole, ordered chicken burger. You know what? Let's do something a little bit more healthy, maybe chicken bowl. Yeah. And also note, here we have tracker running. And in producer, I'm gonna do run producer. There you go. A new event was added. And if I move back to the tracker, you see that it immediately polled and got the new event of the new order. There you go. So every time a new order comes in, the tracker is basically polling to see, is there a new event? And once there is, it reads it out and does something with it. So now there is one final thing that we are going to optimize in our code. So let's observe now. So tracker, let's stop the tracker. And as you see, when we stop the application, we have this, it's more like a warning or like a message about ungraceful or not clean termination of a program. So what we're going to do is, again, this is important, especially for production environments. We're going to add a logic to gracefully shut down our consumer, Kafka consumer application. So in case it crashes or it gets restarted or stopped, whatever, to make sure that everything gets cleaned up, just like we did with producer, right? So we have this flush to make sure the producer doesn't hold any events that it hasn't sent yet to Kafka. The same way, we're going to make sure that when the consumer application stops or crashes, everything gets cleaned up, so to say. The connection, which is, open and polling from Kafka, is shut down gracefully. The application stops gracefully, and we don't have this keyboard interrupt trace. This is actually a Python issue. So Python raises this special error called keyboard interrupt whenever we manually stop script. And this exit code and this message here basically just mean that program was ended by you, not by an error in the code itself. So it was manually ended. But more importantly, in addition to that, we also want to make sure that when the program ends, when the consumer program ends, whether manually stopped or program crashed or whatever, the consumer connection to Kafka is always cleanly closed. Because if program crashes while consumer connection is still open, while it's polling for new events, it can lead to things like resource leaks or issues on the server and so on. So in real production environment, closing consumer connection when program stops for any reason, it's kind of a must. So we're going to cover that here as well. So combining all this, graceful shutdown here and closing connection, we're going to add a optimization here. So we're going to wrap this around with a try catch block. So we're going to run this in try, or try except in Python. And if there is an exception, such as keyboard interrupt, this is the name of the exception here. So in this case, we are just gonna we're gonna catch that error, so to say, and we're just gonna print out a statement. Basically, let's again use our emojis. Let's do something red, not a broken heart, but maybe this one here. Yeah, let's do like stopping consumer, something more elegant than this trace here. So that's just gonna take care of, shutting down the application manually. And this is an important one. We're gonna do finally. So whatever happens here, right? Whether it's in the try, a crash, whether it's an except, or maybe some other exception, an error that happens other than this one, we want to always close the consumer connection. So this thing that we're initiating here, we want to close it whatever happens in this block. And that's it. That adds that final optimization. And again, let's run this now. And as you see, it doesn't print out anything because it has already read all these events in the orders topic. There's nothing new. So it just waits for new stuff to appear. And if I again simulate, let's say another user orders 10, let's call it Lara. Let's say Lara orders 10 frozen yogurt, something like this. And let's run it again and check the tracker. Again, it prints out or reads that event. And now if we stop the tracker, let's see what happens. It just says stopping consumer, process finished with exit code 0. All fine. Awesome. So now we have a working producer, a Kafka broker in the middle, and a consumer. So producer, broker, consumer setup, end to end. And messages are flowing through Kafka in real time, which makes it a very simplistic but also realistic end-to-end setup for a Kafka application. I really hope you enjoyed this tutorial. I hope you learned a lot and you feel like this hands-on practice actually made a lot of the concepts demystified for you, especially seeing this end-to-end process from start to finish. If you did get a lot of value from it, then make sure to pay it forward and share it with one colleague or friend who you think might be interested and will benefit from this skill set as well. So thanks for learning with me, and I'll see you in the next video.